I'm really excited to be up here. Thanks to Arturo for the great previous talk. I think that some of that adversarial and edge cases that you talked about in the previous one should help some of these concepts resonate a little bit. Let's see, the big green button sends us forward. Cool. So a little bit about me. I've worked on computer vision products for defense and security customers, some recognizable names. Where most notably was the head of product at a company called Synapse that was building a vertically integrated detection system for security, where you can see there, that's me, an old picture of me with our first automated threat detection system installed in an airport checkpoint, which I then proceeded to babysit for the next 3 months, watching it detect good things and bad things. I worked at Palantir working on AI products, mostly for the defense space, and then most notably co-founded Kalena, where we've helped build proper testing processes for companies across different domains in computer vision. But these things that we'll talk about, test-driven model development, we'll use examples for computer vision primarily, but the same structure applies for any domain. So the main thing really that I've learned is that you can't trust ML to work as expected. To illustrate this, we'll look at a case study where we have an ML team that spent months improving statistical evaluation metrics for a model. This is an object detection model where we're trying to detect these prohibited items in security X-ray scans. We'll look at an image like this. This is an X-ray scan of a gun. It's very obvious. This team presented a new model with a 99% F1 score, and in that is a greater than 99.5% recall, which if you would just interpret these statistics directly, you would expect that it'll catch 199 out of every 200 threats, and you'd probably also infer that the one threat that it missed out of those 200 is going to be very hard. What we actually saw when we deployed this in the field was that the model missed a very obvious gun, pretty much exactly like the presentation here on the right. When we first installed the system, we'd been installed at various places for a while at this point, and the first thing that anybody does, they say, oh, let's see it work. So they put a threat that they have around them through the machine in a bin, and they want to see the box around it. So this model missed this very obvious gun, and that spun out a ton of consequences for us. There's lost trust from the customer, which if you say your model does something, you say your ML product does something, and then people see it do the opposite thing in what they consider to be a very easy circumstance, then that trust is gone, and it can be very, very difficult to build back. This internally led to a very long time spent investigating, validating that yes, this lost behavior, this regression exists, collecting new data, retraining, and compiling reports to convince people, convince the stakeholders that we solved this problem. But this entire process doesn't guarantee that this bug isn't going to come back, that this behavior isn't going to be lost at some point in the future. Because all we did was follow industry standard practices where we collected a bunch of new examples of guns presenting like this, put them in our test set, and our test set is hundreds of thousands of images. And what we're really doing to make decisions about whether or not we should deploy a new model, whether or not a new model is better, is just looking at that top level F1 score, which of course doesn't tell you, does my model detect this particular case? So this is a shortcoming of the current ML evaluation approach. You spend a lot of time collecting data. You put together some test data set. You usually freeze that test data set for the duration of a training period. You train a whole bunch of different models, and you watch them converge in graphs like this in the middle. And then you promote these models to testing, and you run them across this aggregate benchmark, and you get a number like that, 99%, which doesn't actually tell you the things that your model is going to do and the things your model is not going to do if you were to deploy it out into production. One of the main reasons for this is a phenomenon called hidden stratification. Hidden stratification is, in short, there are easy cases and there are hard cases. For a given class, let's say gun, there are ways that it presents that are obvious. There are ways that it presents that has a high level of difficulty, high level of occlusion perhaps, and the thing that your model is trying to detect, let's say a gun, might have very highly variable presentation and thus performance from your model. The paper that coined this term was reproducing a result from another paper on classifying the presence of lung cancer in X-ray scans. And they reproduced it. It's that blue line, that middle ROC line, which is relatively good performance. You know, it's not perfect. It's not up in the corner and square, but it might be useful in a clinical setting. And then when they actually looked into it, they saw that the high performance This yellow line above the top ROC curve there was in cases that had other things in the image. It had, in this image in the right, we have a chest drain, which is a palliative measure that means that they've detected your lung cancer, they're treating you for it, and they don't need your new model to detect lung cancer. For X-ray scans that did not have this chest drain, for the important case, for the people who aren't already being treated for lung cancer, the model performance was very low. This is barely better than a random guess. And what they found here, this is a particularly dramatic example that illustrates why looking at just the top level metric is insufficient, because you're gonna have highly variable performance across these different subclasses. This paradigm leads to a world where when you're building an ML product, important questions to your product are very difficult to answer. If you're involved with this process at all, as a developer of these models, you're training them, you're a product manager trying to meaningfully lead this effort, you're a leadership stakeholder who's staking the company or his team on the success of this product. If you're on the other end and you're buying these products or you're having one of these ML products installed in your facility, you've probably been on one or both sides of these questions. Things like, I have a new model. Where does it succeed? Where does it not succeed? What are its failure modes? When can I expect it to not perform? What, between one model and a new model, what is improved and what is regressed? Are the behaviors the same? If I have a number on my aggregate benchmark data set that went from, let's say, 96% F1 score to 99% F1 score, is this improvement uniformly distributed across all scenarios? Did I improve everywhere? If I have multiple models, which should we deploy given the circumstances of a particular deployment? And finally, this is a particularly difficult one to answer for a lot of people. How do I know if my model is ready to be deployed? Do we have an ML system that does what we set out to do? Or is it just a best effort that ultimately falls short? And this can be a very difficult question to answer when you're building ML products. The way to answer this is with a paradigm shift to test case-based evaluation. The current world, where we have a soup of all sorts of different scenarios in our test set, and we're computing one number from this test set, in test case-based evaluation becomes an orderly array of different scenarios that you care about performance in. Rather than computing your top-level benchmark metric, you might still do that, but you'll also compute metrics across each of these different subsets of your data to understand how you're performing, particularly in these different subsets. And this allows you to make, informed decisions about what you're gonna do and whether or not a new model that your team's come up with is worthy of being promoted to production. So high resolution test results get you out of this world where model A is your previous model. It has a 97.8% F1 score on your test set. And model B is your new model. Your team's very proud of it. They spent weeks training it. It has much higher numbers, 99.2% F1 score. Right now, if you make this decision, you're gonna deploy model B. This is the information that you have. It has a higher number. With test case-based evaluation, you have a detailed report card that allows you to make an informed decision. Model A has good performance here across these test cases, empty bin, back view, front view, that are very important or even critical for our product. We can't deploy a threat detection model that doesn't catch the easy case that people are always going to run it through first. That's a critical thing for our product. And we have very low performance in some ultimately non-critical or unimportant scenarios. This new model has pretty good performance across a lot of these important scenarios, and it has really gained a lot in these edge cases, in these more difficult, more adversarial, non-critical ultimately to your product, but we've improved on them maybe because we still care, but we care less about good performance there. But this performance, this gain over here, came at a regression in a very critical case for us. And if we're looking at this top level metric, we make the decision, ship that model out, without the understanding that we lost a behavior that we used to have, that we used to perhaps rely on, a behavior that customers would never consider would go away. And if it goes away, they think your product's broken. This brings us to the pattern of test-centric ML model development. This isn't really a new development pattern. It's just a newfound emphasis on the already central role that tests play within your ML org. Tests are how you actually communicate what your model does before you push that model into production. Tests for your ML engineering team are the target that they're trying to improve on. Tests are the only meaningful way to gauge that team's output. For product management, tests are the only way that you can express the scenarios that you expect to succeed in. Product management needs to decide, they're not going to ask the ML company if we're making a threat detector, let's say we're, for something a little bit more understandable, let's say we're making a car detector. They're not going to say, I want to detect every car ever. That's like telling a software engineering team, I want an application and I want every feature. You can't do that. You're going to get something that's buggy. You're going to get something that's subpar. And so product management needs the ability to say, we need a car detector that works for cars that are within 100 meters of our sensor, that work at these lighting levels. If the car doesn't have its tail lights on and it's nighttime, it's okay if we don't detect it. And product management defines these test cases that enumerate the behaviors that they expect the product to have. And so these tests allow them to meaningfully guide product development. For anybody that's on the non-technical side of the organization, non-technical or leadership, the only thing that they know about these models prior to pushing them into production is from these tests. And so tests communicate the behaviors that you do and you don't have. Tests allow you to deploy in situations that you know you'll succeed in and avoid situations that you'll fail in, or retrain such that if you know you're going to fail in a situation, you now have a new model that doesn't have those same shortcomings. So everything that you know, that you learn prior to pushing to prod is learned from tests. And if you're in a situation where performance matters, where you're really trying to make a product that succeeds, that does something, that automates some job, you need to know a lot before you push things into production. If people are relying on your system, you need to learn a lot before you hit the go button and send that model out there. So this really comes together to mean that your testing data is actually the most important data asset that you have. Your training data is ultimately an implementation detail. Your training data imparts these learned behaviors on your models, and it's necessary to do that, but your training data itself doesn't really provide value. It doesn't tell you, I do this thing that I thought I did, or I don't do this thing that I thought I did. Your testing data is the rubric against which you evaluate these models. And in a world where you need to have this fine-grained understanding of performance, your testing data is the thing that provides you with more value than your training data. In the testing world, with a test-centric ML model development pattern, the constituent components are pretty understandable and should be pretty familiar. You have unit tests that produce a behavioral report card for the different scenarios that you want to succeed in. Let's say product management decides that our product needs to succeed in scenarios A through G. This is what our product does. We can evaluate performance in scenarios A, B, C, D, E, F, G, and bucket those results into qualitative buckets that communicate in a very understandable way what your product does and what it doesn't do. And these unit tests allow you to say with a new model, I have excellent performance in scenarios A, D, and E, and improved performance in A, C, D, and F from my previous model. This tells you at a glance whether or not you can deploy this new model or you should deploy your old model, because you might think, okay, my deployment is scenario B heavy, and this model has gotten worse in scenario B and worse in scenario G, so maybe I shouldn't deploy it to a deployment that heavily relies on those two scenarios. Communicating with metrics and saying this new model has a 97.1% F1 score is meaningful only as far as you understand the data set that number was computed against. If you don't have an intimate understanding of that, then that number is effectively meaningless. You're taking it at face value that when your team tells you this number went up, you say, okay, that's a better model. But when you have test case-based evaluation, you can communicate in terms of behaviors. The non-technical members of your team, the people who understand intuitively how users are going to interact with your product, the people that understand what it means for your computer vision product to succeed or fail, these people need to have the understanding of the behaviors that model has, and they usually don't have the high level of visibility or contextual understanding on your test set that your ML engineers are going to have. So putting together a qualitative report card like this greatly increases the bandwidth of communication of what that model actually does beyond the ML engineers who are responsible for training it. Another key component of test-centric ML model development is regression tests. Regression tests in software engineering operate pretty much the exact same way. where you identify a regression, you reproduce that. For machine learning, what that means is you generate a subset, a test set of some meaningful number of samples or images, that depends on your domain, and you validate that the behavior is not there. So, for this missed gun in an empty bin, we'd collect a couple hundred images, or we'd mine our data set for a couple hundred images, and we'd recompute metrics across that subset and say, yep, our F1 score is like 40% in those cases. And now that bug has been reproduced. We can meaningfully go and try to fix it and deploy a model that doesn't have that same bug. However, if we don't put together these regression test suites where that subset of data that we just computed to validate the existence of this bug, if next iteration we just throw that data back into our aggregate benchmark and shift our focus somewhere else, then we're playing whack-a-mole, perhaps, and that bug might reappear because we've lost our thumb on it. We're no longer looking at this particular case. So a regression test approach involves each of these bugs that pops up, and in our Turo slide, some of these bugs might be these weird shaped things that you'll see on the highway. Different items along the long tail of edge cases that probably characterize your domain. You create these regression tests for them such that when you're focusing on, let's say I'm an autonomous vehicle company, I'm getting better at this quarter, I'm getting better at flatbeds, I'm getting better at pedestrians on the side of the highway, and I'm getting better at oversized loads, right? This is my push this quarter. This is what we're gonna get better at. If I create regression tests that now go into a test suite that every new model for every quarter going on in the future runs against those, it ensures that next quarter, when I've moved on to dirt bikes, I don't regress on oversized loads because I'm no longer focusing on it. This is pretty necessary in efforts to chase down the long tail of edge cases. And I feel like most domains I think, are characterized by a lot of low-hanging fruit that you can pick pretty easily, and then a long tail of edge cases that are increasingly difficult and increasingly uncommon, but are nonetheless necessary for you to actually succeed at what you set out to do with your ML product. Integration testing is also a very important part. It's very common for the model itself, the runtime environment, and the data that you're feeding through it to differ significantly between development and deployment. If you're not doing integration testing that runs in the actual deployment conditions, it's effectively the same thing as just saying LGTM locally, when you're developing software and shipping it out into production. Conditions are different there. You need to understand if this still performs at the expected levels when you have deployment conditions. And some of the reasons why these conditions differ are things like optimization for the edge, quantizing your model to use uint dates, running on any of these runtimes that is going to probably be different from the PyTorch that you trained your model in, pre and post-processing systems, ways that you tile your images and then splice predictions on those tiles back together, the scaling of the images themselves. And then, most importantly, finally, the shift in data format or data distribution. If you collect a lot of data that looks one way, and then you deploy, let's say you're collecting these data on 1080p videos, and they're very well annotated, they're very clear, the camera's always clean, and then you deploy on grainy cameras on the edge that are running at 480p. You need to make sure that you have testing data, integration testing data, that exactly mirrors those deployment conditions. Otherwise, you might see really unexpected behaviors, and the numbers that you have in your performance report are effectively meaningless because you've said, okay, these are under completely different conditions than what we're actually deploying in. And that sends you scrambling. The final important part of test-driven model development is end-to-end testing. Typically in the field, you have ML products that are much more complex than just a model operating in isolation. You have these pre- and post-processing functions talked about last slide. You will often have a model pipeline that is feeding results from one model into the next model, where you're trying to solve this problem that's more tricky than, say, a single object detector can solve. So you architect these broader systems that have models as components in it, but the overall thing is some business objective that no one model can do. So testing that whole end-to-end system is quite critical. To illustrate this, we'll look at a case study that our research team put together on the Joint Attention in Autonomous Driving JAD dataset, where you have video snippets that look like this with annotated pedestrians and the actions that they're doing. So the gray bounding boxes are ground truth labels for pedestrians in that frame, and they're annotated with whether or not that pedestrian is crossing or about to cross. So I'm not sure you can read it here, but these labels up top are saying is crossing. So we have these ground truths, and the way that we're building this model that we're building is attempting to identify pedestrians that are currently crossing or are about to cross. In other words, collision risks, pedestrians that we need to be aware of and potentially adapt to in our behavior because they might suddenly show up in our driving path and we need to take defensive action, slow down or swerve out of the way. So we want to be detecting these pedestrians ahead of time such that we can take defensive driving actions before things become drastic. The objective of this model is to reduce that collision risk in this AV scenario. So the way that we solved it is with this pedestrian detector/tracker model. We tried two open source models here, SORT and DeepSORT, which was detecting these pedestrians and assembling these tracks, stable detection IDs across frames, and feeding these tracks into a classifier that's trying to decide whether or not this track is crossing the street or about to cross the street. And we use two different ones there, so it's making that final binary classification. When we evaluated these models in isolation, we saw that the DeepSORT model was pretty much across the board, across all different scenarios, the better upstream detector/tracker model, and the C3D model was the better classifier downstream model. When we plugged the whole thing together and tested end to end, we found that the pipeline with the less good, the lower performing pedestrian detector feeding its tracks into the better classifier actually produced the lowest collision risk. All of the tracking and detection metrics that we looked at indicated that DeepSORT was a better model. But when we finally plugged our whole product together and evaluated our KPIs, which is identify the most collision risks so that we can slow down and take defensive action, when we evaluated the full thing with that KPI, we saw that actually most of the performance gains that DeepSORT had over SORT were gained in scenarios that were unimportant for our product. They were far away pedestrians that were not a collision risk because they're not near us. They were pedestrians that were not crossing, that were on the sidewalk and maybe were being occluded frequently by telephone poles. For the important scenarios, the pedestrians that are close to us, in front of us, and crossing, SORT performed better. And the only way this became apparent was when we plugged the whole pipeline together and tested our overall objective. Because only our collision risk, when we take into account all these factors like how far away the pedestrian is, only when we tested for that KPI did it actually become evident that the best comparison, the best model pipeline for our particular task that we set out to do wasn't the one with the highest metrics. So test case-based valuation and a rigorous testing platform allows you to set up a global metric. We've been maligning global metrics a lot, but they're not all bad. You can set up a global metric, a one number that you can use to make go or no-go decisions. This one number can be fed into continuous delivery systems such that you can properly set up model deployment systems that kind of mirror what we've had in software for a very long time. Such a global metric that actually reflects your product goals would perhaps look something like this, where you have the performance on each of these different scenarios. Let's say that's F1 score across each of these different subclasses, each of these different scenarios, and some product value coefficient that somebody has come up with to assign to those scenarios. In this gun detector example here, we can look at the performance from this model A that we looked at earlier and the product value coefficient that we've assigned to these different test cases based on how critical it is that we have this behavior in production. And then we can feed the results from model A, the F1 score of 97.8, and model B, the F1 score of 99.2. We can feed them through this system and see that this has correctly identified that model A is the better model, and despite the higher F1 score across our aggregate test set, model B does worse at our product objectives and should not be deployed. What we have here is a pretty simple linear sum of performance in different scenarios, but in a lot of domains, it's not just overall performance that matters, it's variance in performance across different subsets, bias. And so this provides you with the ability to also add, let's say, a penalty term for variance in performance across different demographic subsets. If you're developing a face recognition model that has a higher overall score than your previous one, but it turns out that most of those gains were in some demographic buckets and they came at performance costs to other demographic buckets, penalizing that variance in performance will help you avoid that situation where suddenly your model blows up and doesn't work for certain demographics. So this kind of framework is pretty critical to deciding meaningfully whether or not a model should be deployed. And I would like to wager that most product managers or most product owners for ML products that are out in production right now have some informal understanding of the coefficients that they would assign to these different circumstances. They know what's important and they know what's not important. You know, the AV product owner who's deciding to do the pilot in Arizona knows that product performance in sunny is extremely important, and product performance when it's super snowy or rainy is not really that critical to the success of their product. So weighting both of those scenarios the same is not something that you should do. So this exercise formalizes this concept that's probably already there in somebody inside your organization and really allows you to think critically, what are we actually trying to set out to do? How do we do that? Understanding that perfect performance is never going to happen, where is it most critical that we perform well, and where is less critical for our product? And that can allow you to iterate in such a way that you're actually making the biggest impact every time you're training a new model and you have a better thing that you want to deploy to production. Iterate effectively. So this rigorous ML testing system is quite hard to implement, and having a successful ML product is not something that a 10x ML engineer finds a groundbreaking new architecture or some crazy new way to splice in synthetic data and finally they have a model that performs perfectly. It's a slow and iterative process that requires you to have a system for these tests. If you don't have such a system, it's time consuming, it's tedious, and it becomes quite difficult to manage. So most teams don't expend the effort and just hope that things get better when that one number goes up. We built Kalena to make this exact kind of testing easy and accessible to anybody that has models in production. And if you want to hear more about that, stop by our booth. Happy to chat with anybody. But thanks for coming, everybody. And if we have any questions, I would love to answer them. Yeah. 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 So we found, I think, two interesting things from talking with teams that are interested in setting up these systems. The first is that most teams have been labeling more than is strictly necessary to train the models that they're currently using. The marginal cost to adding more fine-grained tags to, let's say, an object label when you're labeling it is relatively low. So teams are already using this richer labeling as a part of their current process. So that's one thing that we found is actually quite common. The second thing is that if you're a mature team, if you have a product that's in production, you probably have a lot more metadata about your images that you're using to train and test than you know what to do with. You have metadata that characterizes where it came from, who labeled it, what the composition of the labeled items inside that image is, when you collected it, all of these important things that you can use to create meaningful test cases that reflect your domain quite well. And then if that's not enough, the results from previous models are often extremely effective, especially when you take things like common failures that my last 4 generations of model that I've deployed to production. When you take sort of set logic like that, you can very easily stratify your data into these different test cases in a way that reflects difficulty in your domain quite directly.
But I guess it's not quite as necessary to have that data in your training set. It's more like,
Yeah. 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 Any questions? Yes. Oh, yeah. So I think we plug it all together with a CI system. You can tag these different test cases. And whenever you've run new tests, you can kick off a job that pulls down those metrics across these different test cases, and you can splice in your coefficients at that point. You can even tag these test cases with those coefficients to come up with that overall go or no go. Yeah, so the way that we typically like to do that, we have a Python client that allows you to pull down all this information that you've pushed up about your model's evaluations, pull that down in a CI job in a script, and then apply this combination logic with your coefficients to decide whether or not this new model should be deployed. Yeah. Yeah. So the really important thing with testing this end-to-end system is you have this end-to-end evaluation, but you also have each of the components evaluated in isolation. So you don't need to run this model that exists at one point in your pipeline multiple times. If it's a part of multiple pipelines, you can just plug these components together and you can view the end-to-end performance. And then when you see something really weird, like poorer performance from a better upstream model in your pipeline, you can zoom in to the particular upstream model's performance and look at the way that you've stratified those test cases and find, okay, actually, for close pedestrians, this is the place that we're performing more poorly in. So having multiple zoom levels, the one that you can kind of go to given the current task, your end-to-end zoom level, your individual model zoom level, and then your individual images or videos or whatever they are, being able to zoom to the right level to answer the question that you have right now is very critical. Great, well, thank you everybody.